A second important case is the Gamma-Poisson Conjugate families. In this case, the data come from a Poisson distribution, and the prior and posterior are both gamma distributions. The Poisson random variable can take any non-negative integer value all the way up to infinity. It is used in describing count data, where one counts the number of independent events that occur in a fixed amount of time, a fixed area, or a fixed volume. The Poisson distribution has been used to describe the number of phone calls one receives in an hour, or the number of pediatric cancer cases in a city, for example, to see if pollution has elevated the cancer rate above that in previous years or for similar cities. It is also used in medical screening for diseases such as HIV, where one can count the number of T cells in a tissue sample. The Poisson distribution has a single parameter, lambda, which is both the mean and the variance of the Poisson random variable. The probability mass function for the Poisson is lambda raised to the power k over k factorial times e raised to the negative lambda power. This gives the probability of observing a random variable equal to k. Here, k factorial is k times k minus 1 times k minus 2 all the way down to 1. And obviously, lambda must be greater than 0. It is both the variance and also the average of a count. Famously, von Bortkiewicz used the Poisson distribution to study the number of Prussian cavalrymen who were kicked to death by a horse each year. This is count data over the course of a year, and the events are probably independent, so the Poisson model makes sense. He had data on 15 cavalry units for the 20 years between 1875 and 1894 inclusive. The total number of cavalrymen who died by horse kick was 200. One can imagine that a Prussian general might want to estimate lambda, the average number per year per unit, perhaps in order to see whether some educational campaign about best practices for equine safety would make a difference. And suppose the general is a Bayesian. Introspective elicitation leads him to think that the lambda is about 0.75, and his uncertainty in this belief is expressed as a standard deviation, would be 1. Since this time period antedates the era of modern computing, the general will need to express his prior as a member of a family conjugate to the Poisson. It turns out that this family consists of the gamma distributions. Gamma distributions describe continuous, non-negative random variables. As we know, the value of lambda in the Poisson can take any non-negative value, so this fits. And the gamma family is pretty flexible. One can see a wide range of gamma shapes. The probability density function for the gamma is indexed by two parameters, k and theta. But be warned that some books parameterize it in a slightly different way than we shall use here, and you should always check which parameterization is being used. For our parameterization, the mean of the gamma is k times theta, and the standard deviation is theta times the square root of k. So the general's prior is that there's the gamma such that k times theta equals 0.75, and theta times the square root of k equals 1. Solving these simultaneous equation shows that the general's k is 9/16 and the general's theta is 4/3. For the Gamma-Poisson Conjugate family, suppose one observes data that are Poisson distributed with values x sub 1, x sub 2, ... x sub n. Then, in the same way that we recognize the kernel of the beta distribution in the integral form for Bayes' rule for the beta binomial family, we would recognize the kernel of the gamma when using the Gamma-Poisson family. It turns out that the posterior gamma has updated parameters k star and theta star, where k star is k plus the sum of the observed values, and theta star is theta divided by n times theta plus 1. For this data set, there are n equals 15 times 20, or 300, observations, and the total number of cavalrymen who died was 200. Therefore, the general now thinks that the average number of Prussian cavalry officers who die at the hooves of their horses follows a gamma distribution with parameter k star equal to 200.5625 and theta star equal to 0.0033. How has the general changed his mind after seeing the data? Before he saw the data, he believed that lambda was about 0.75. Now he believes it's about 0.67. And before he saw the data, his uncertainty about lambda, expressed as a standard deviation, was 1. After seeing the data, his uncertainty has shrunk to 0.047. What have we learned? We learned a new pair of conjugate families, the Gamma-Poisson. To do that, we had to learn about the Poisson distribution, which is a useful model for count data, and about the gamma distribution, a flexible family of distributions for continuous, non-negative random variables. We learned the updating formula and applied it to a classical, and I hope memorable, dataset.